Okay, so we mostly talked about vacancies so far. So the same principle really applies to any other types of point defects. So to form a point defect in a material, you always have to invest certain energy, which is called an activation energy. And for example, if instead of vacancies, we talk about interstitials, then typically this activation energy is significantly higher. So what that means is that to form or take an atom and place it into the crystal structure, it's much more difficult than to take an atom and remove it from that crystal. And for that reason, the equilibrium concentration of interstitial atoms at a given temperature are typically significantly lower than the number of the vacancies. So this is the reason why all of these measurements that I indicated are actually growing. So the number of the vacancies is changing, but you're also starting to introduce these interstitials, but the concentration of the interstitials is significantly lower than for the vacancies, right? So in general, the vacancy concentration is significantly higher. So what I just told you is that basically the enthalpy of the formation for an interstitial is significantly higher than for a vacancy. So this was just a mathematical way to summarize what we just mentioned. Okay, so what we learned so far is that at a given temperature, for a given material, there will be an equilibrium concentration of the point defects. However, if you take a piece of a material, and if you measure these point defects, that can be relatively different from what you would predict from the equilibrium compositions. And that strongly depends on the way how that material is processed. So you can introduce either vacancies or interstitial atoms in different ways, except for simply increasing their temperature. So for example, if you take a piece of a material and you anneal it, and then abruptly quench it, then what will be the concentration of the point defects, let's say vacancies in this material, relatively to the equilibrium concentration at that temperature? Let's say that you take a piece of a material, you ramp up the temperature to 1000 degrees, and you cool this material very quickly. So now you're at room temperature, right? You can calculate what should be the concentration of the vacancies at the room temperature. How would the concentration in this material that we quenched compare to what you calculated? It would be much higher. And it would be, why would it be much higher? Can you explain?
Because you kind of like tricks the material to think that, like when you heat up, you create a lot of vacancies. When you cool them so quickly that they don't have time to go back to where the vacancy is.
Exactly. So at a relatively high temperature, the concentration of the vacancies is higher than at room temperature, right? And if you cool down the material very quickly, you freeze that material in that particular state, right? The atoms do not have enough time to diffuse to their thermodynamical equilibrium position. So, and how do you then equilibrate it? So you have that material that was quenched. How do you then reduce the density of vacancies in that material to be at the equilibrium at that particular? Yes? You heat it up, and then you just cool it down slowly, right? And you just leave enough time for the system to get the equilibrium concentration. Another possibility to introduce point defects is to use irradiation. For example, you can use very high energy electrons, neutrons, positrons, etc., to simply remove the atoms from the material. In this way, you can produce non-equilibrium concentration of defects. You can use, for example, ion implantation. So if you use ions, then you can implement the atoms within the material itself. Cold working is simply plastically deforming the material multiple times, and then in that particular ways, you can introduce different types of defects. And we will see that cold work is particularly important for when we consider dislocations. So the same thing can be also thought about. So we mostly talked about metals and removing individual atoms. But if you have solid solutions, what that means is that you're simply introducing different types of the atoms in the crystalline structure. So an example here would be copper in nickel is the substitutional impurity, or we already mentioned carbon in iron as interstitial impurity, and in the first case, substitutional impurity atom. So very often you can, when the concentration of these atoms is relatively low, you consider them to be point defects or individual defects, but the concentration itself can be increased such that you form a different phase. So if the concentration of the point defects in this particular solid solution increases in a way that the concentration is relatively high, you can start completely new phase. And there is a simple way to predict whether one particular material will be forming these types of extrinsic type of point defects in a given material. And this is described by so-called Hume-Rothery rule. And it's a very simple rule that states that in order to predict whether the material will form point defects in a given material, there are 4 different criteria that it has to satisfy. So the first one is that the change or the difference in the radius between 2 atoms is less than 15%. So if you're introducing nickel into copper, you calculate what is the difference in their atomic radii, and if it's less than 15%, then you can say that this material would likely form a point defect. The second is the proximity in periodic table. What that means is that they should have similar electronegativity. The third requirement is that they have relatively similar crystalline structure. And the fourth is the valence. So that's basically a set of empirical rules that tells you how likely is that one material will form point defects in a host crystal. So the first thing is that you look at the radius, then you look at what is their position in the periodic table, etc. So if you can apply this rule, and I can ask you a question, if you have this set of properties, you have atomic radii, you know the crystal structure of different materials, their electronegativity, I can ask you a question, whether nickel or silver will more likely dissolve in copper. So this is the copper, so we have properties of copper, here is nickel, and we have silver. So which of these elements will more likely to dissolve in copper based on the rules that we just described? I'm sorry? Okay, why would that be the case? That's the correct answer. Yeah? It follows all of the rules, right? So the radii are very similar. They have similar crystalline, actually the same crystalline structure in the pure forms, relatively similar electronegativity, and the valence is similar. And in fact, copper and nickel are purely or completely soluble. So I do encourage you to check out the phase diagram of these two materials and check if they're actually fully soluble, and you will see that they are. Okay? So just pull out, so this would be nickel. And in fact, silver and copper are soluble to the approximately 18%. And again, I do encourage you to check out the phase diagram, and you will see that that's true. Right? So simply by applying this set of rules, you can predict how the phase diagram of two materials would look like, at least two metals. Okay, so with this, we will complete the discussion today, and what we will do on Monday is we will extend this discussion to ionic crystals. So we mostly talked about metals, and where you don't necessarily have to think about the charge, right? So on Monday, we will talk about the crystals where when introducing a certain type of a defect, changes the balance of the charge. And then you have to compensate that to keep that charge neutrality. Okay? With this, we will stop and have a nice weekend, have some sleep, and have more energy on Monday. Okay?